We're still in section 2.3, and we're talking about dividing polynomials. What I wanted to do, we're going to talk about factors and remainders. What happens? What does our remainder tell us when we divide? And how can we use? Why do we want to divide polynomials? What does that tell us about polynomials? Let's see. The first thing I want to do. I think I wanted to do another. Which time do we have? All right, so if we have time at the end, I'm going to do another couple of examples, or another example at least, of doing long division. But during the course of what we talk about today, we'll do synthetic division a couple of times. So what we're talking about is what does the remainder when we do synthetic division, when we do long division, but more specifically when we do synthetic division, what does the remainder tell us? And how can we use that to actually solve problems by doing these division problems? So the first thing we're going to talk about is the remainder theorem. The remainder theorem says that if we divide a polynomial, some f of x that's a polynomial, by x minus k. So we're dividing by x minus k. We can use synthetic division. If we divide this polynomial by x minus k, the remainder is, I'm going to say R is a remainder, is the function evaluated at k. So when we get a remainder, that tells us the value of the function if we plug k into our polynomial. So that's one way that we use the remainder when we do synthetic division. And this can come in handy if, for example, on a quiz or on a test, we have this long, complicated polynomial, and the problem tells us to evaluate the polynomial at x equals 7. So we can either plug it into our calculator and do 7 to the 5th times 5 minus 7 to the 4th times whatever, and calculate the polynomial, or we can do synthetic division and find the remainder. So an example of the kind of problem that you would see with this is, the kind of question you'd be asked is, we're going to use the remainder theorem to find f of 1 when f of x equals x to the third minus 2x squared minus 4x plus 1. Now this one, it wouldn't be too hard to plug in 1 and evaluate this function at x equals 1, but we're going to show how we use the remainder theorem. So what we're going to do is divide by x minus 1, and we're going to use synthetic division. So we're going to put a 1 out front. What's that? So the remainder theorem tells us the remainder f of k is the same, the remainder we get when we divide by x minus k is the value of the function at k. So here k equals 1. So we can find that value just by dividing this function by x minus 1. So for synthetic division, we're going to put the 1 out front, and I'm going to write my coefficients in reducing powers of x. So I have a 1, negative 2, negative 4, 1. Bring the 1 down. So bring the 1 down. 1 times 1 is 1. Add these. I get a negative 1 here. Negative 1 times 1 is negative 1. Add these. I get a minus 5. 1 times minus 5 is minus 5. Add these and I get a minus 4. So the remainder equals 4. So f of 1 equals 4. I'm sorry, negative 4. I do have a negative sign there. So this is a really easy example, but if we had a complicated polynomial with like a 7th power, and we're evaluating that at f equals 7, we can do synthetic division and do multiplication and addition instead of doing all these exponents and multiplication and subtraction to try to evaluate that function. So to evaluate a function at a particular value, if our function is a polynomial, we can use synthetic division, and we're dividing by x minus whatever that number is that we're trying to find. Questions on that example? So that's one way we use synthetic division, is to evaluate a function. We use the remainder theorem to evaluate the function. The second way that we use synthetic division is probably the more important way or more powerful way, is what we call the factor theorem. And the factor theorem tells us that a polynomial and we have our polynomial some function of x has a factor of x minus k if and only if f of k equals 0. So what the factor theorem tells us is that if we divide our polynomial function by x minus k, and the remainder is 0, then x minus k is a factor of our function. And the other day we talked about a couple of different things. I mentioned a couple of different things that were equivalent to saying that x minus k is a factor of this function. Does anybody remember what some of those equivalent things were? X minus k is a factor. We said that was equivalent to saying k is a 0 of f of x. That means that f of k equals 0. Another equivalent way that we can say this is that k is a solution of f of x equals 0. That's an equivalent way of saying this. The third equivalent way is saying k is an x intercept of f of x. So all of these four things mean the same thing. X minus k as a factor is the same as saying that k is a 0 of the function, meaning f of k equals 0. K is a solution of f of x equals 0, or k is an x-intercept of my function f of x. And we figure this out by seeing if, when we divide our function by x minus k, the remainder is 0. So that's how we tell if this particular value of x is a solution to our equation. So this is really the most powerful thing that we can, one of the most powerful things we can use synthetic division for, is to figure out if we have a solution to our equation when our equation is a polynomial. So let's look at an example of how we're going to use the factor theorem. And this is really the biggest application of synthetic division. We want to show that x minus 1 is a factor of f of x equals x to the fourth minus 1. That's an f. So this one's really easy. We want to show that x minus 1 is a factor. Well, what does factor mean? If x minus 1 is a factor, what does that tell us about x equals 1? This is asking, is x equals 1 a solution of f of x equals 0? Or is x equals 1 a 0 of f of x? Well, what do I get when I plug in 1 for x here? 1 to the fourth minus 1 equals 0. All of these things mean the same thing. So this tells me, since x equals 1 is a solution, x minus 1 is a factor of x to the fourth minus 1. So when the problem asks you if it's a factor, we want to say, is it a solution? Is it a 0? That tells us it's a factor. Now let's talk about how we're going to use this idea. How we're going to use this idea with synthetic division. So this is what factor means that my value of x is a solution. When I plug that value of x into my equation, I get f of x equals 0. So here's how we're going to use this. We have f of x equals 3x to the third plus 2x squared minus 19x plus 6. We want to verify that x plus 3 and x minus 2 are factors then we want to factor f of x. And by factor we mean we want to write f of x equals something in parentheses times something in parentheses times something in parentheses. So when we say factor, we're going to write these three parentheses. So what the question is asking us is kind of two parts, but it's like saying how do we write a number as factors of prime numbers? We can write any number as so 6 is 2 times 3. We can break it down into prime numbers multiplied by each other. Any polynomial we should be able to write as a bunch of parentheses multiplying each other. So that's part of what we're trying to do here. So when our problem asks us this, we're going to use synthetic division. So for my first step, I'm going to divide f of x by x plus 3. If x plus 3 is a factor, my remainder is going to be 0. So let's start by dividing f of x by x plus 3. So I'm going to write my decreasing powers of x. So I'm going to have 3, 2, minus 19, and 6. And x plus 3, that's the same as x minus negative 3. When I use synthetic division, the thing that I'm dividing by has to be written in the form of x minus something. So the number that's going to go in front here is minus 3. Bring the 3 down, and now we're going to do synthetic division. 3 times negative 3 is negative 9. Negative 9 plus 2 is negative 7. Negative 3 times negative 7 is positive 21. 21 minus 19 is 2. 2 times negative 3 is negative 6. And my remainder is 0. So the remainder is 0. So x plus 3 is a factor. Right. That's the remainder is always this last number here. So x minus 3 is a factor. My remainder is 0. X minus 3 is a factor. Now when I did my long division, this is 3x squared minus 7x plus 2. Now I'm going to divide this by x minus 2. And if my remainder is 0, this is going to be a factor. So it's like saying if I can divide 12 by 2 and I get 6, and I can divide 6 by 2, then 2 is a factor of 12 and 6. It's the same idea. I could go back and divide this polynomial by x minus 2, but we want to reduce our exponents. This is going to reduce our work. So I'm going to divide this by x minus 2. So we'll write our decreasing powers of x, 3, negative 7, and 2. And this is set up, I have x minus 2, so I'm going to write a 2 in front. Bring the 3 down. 3 times 2 is 6. get a negative 1. 2 times negative 1 is negative 2. And my remainder is 0 again. So r equals 0. So x minus 2 is a factor. So this gives me, I reduce my power of x by 1 again. This gives me 3x minus 1. So I have two factors, x plus 3, x minus 2, and the last thing that I'm left with is 3x plus 1. So, minus 1. So f of x equals x plus 3 times x minus 2 times 3x minus 1. My factors times whatever I'm left with when I divide everything out.
What happens if they don't work?
If they don't work, then we can't factor it this way. Then you'd say it's not a factor. So what some of the problems will do sometimes is they'll give you one solution. They'll say x equals 1 is a solution, and then they want you to find the rest of the solutions. So I'll pick one of those out of the book, and we'll do that one. And what this also tells us is that the zeros are x equals negative 3, x equals 2, and x equals 1/3. Those are going to be the zeros of the function. That's where the function is going to cross the x-axis. So by finding the factors, by writing them all out, we figure out all the zeros, we figure out the intercepts, so we have some information about what the graph of this function looks like. I said 3x minus 1 equals 0. So I'm setting each of these parentheses equal to 0. So those are the zeros of our function. So let's look at one other example of doing this. I'm going to pick out one of the problems that's similar to a homework problem. So this would be similar to a homework problem. Just want to look at one other type of problem. Any questions here before I move on from this one?
Yeah.
Okay, so let's do one more example. So let me pick one out of the book here. So this works for synthetic division when we're finding factors, linear factors like x minus 1, x plus 2. So let's look at number 57 that Shannon asked about earlier. So this is one of the problems from your homework. So if you write this one down, you have one of your homework problems now. This is number 57. So number 57 says f of x equals 2x to the third plus x squared minus 5x plus 2. And it wants us to verify that these two are factors, x plus 2 and x minus 1. And then it wants to find the remaining factors and write the factorization. So write our function out with a bunch of parentheses. So we're going to start out by dividing by x plus 2. So let's write out our function, decreasing powers of x. 2, 1, negative 5, and 2. And if we're dividing by x plus 2, what are we going to write in front? Negative 2. Do our synthetic division, bring the 2 down. 2 times negative 2 is negative 4. Add these, I get negative 3. Negative 2 times negative 3 is 6. I get a 1. Negative 2 here, and 0. My remainder is 0. So x plus 2 is a factor. This tells me that what I'm left with when I divide by x plus 2 is 2x squared minus 3x plus 1. And I'm going to divide this, divide by x minus 1. So we'll do synthetic division. I have 2, negative 3, 1.
Wait, what is the question initially asking you?
The question asks us verify that these are factors, and then find the remaining factors. So like we did on the example before. So I have a 1 here. Bring down the 2. 2 times 1 is 2. Negative 1, and my remainder is 0. So x minus 1 is a factor. And I'm left with 2x minus 1. So my factorization is f of x equals x plus 2 times x minus 1 times 2x minus 1. My zeros would be x equals minus 2, x equals 1, and x equals 1/2. So those would be the zeros of the function. And that's what the problem asks us to do. So this is a way of factoring polynomials and finding zeros of polynomials. So we can use synthetic division to factor and find zeros. The secret is, the trick is that we have to know one, we have to start out with one factor. We have to come up with one factor initially. All right, questions? Would we like to see another example of long division?
No. We're good.
You're good? You sure? Okay.
And the no wins on you either because you asked. So someone comes in and plays tomorrow.
Having some technical difficulties here, but our homework is on page 140.